Hey everyone, so let's go ahead and get started with talking about the progress of chemical reactions as part of Chapter 18, Section 2. The title of this section is actually kind of weird to me, like progress of chemical reactions. It sounds a little awkward. So I'm going to retitle it myself, because I can do that, and call it Rate Laws. And we're talking about rate laws as a way to mathematically express the rate of a chemical reaction, which we talked about previously. So let's go ahead and get started with rate laws. So let's review a little bit. Let's talk about what is rate. Remember from last time, rate is a measure of how much something changes with a specified amount of time. There are two key things here, change and time. When we have a chemical reaction, change is occurring from a reactant to a product, and that change is occurring along a specified amount of time. So if we have reactant A turning into product B, that rate of how fast it occurs has to do with the change in reactant A over a given time period, so change in time. And delta, again, remember, means change in something. So change in A over a given amount of time. And what we're talking about is how the concentration, and brackets means concentration of reactant A and how that changes over time. So we're really talking about concentration. And so our rate law can be sort of summarized as how the concentration of reactant A changes with some sort of constant, and we call that constant the specific rate constant, and each constant will be specific to the rate of the reaction. So some vocab words would then be the rate law is expression, a math expression for the rate of a reaction in terms of concentration of reactants. And that's multiplied by a specific rate constant, a constant relating to the concentrations of reactants to the rate of the reaction. So to summarize that, we have rate equals K, your constant, times the concentration of the reactant. And there are two different types of rate law expressions. The first one is a first order reaction. In a first order reaction, your reactant concentration is directly proportional to the product concentration. So what that might look like in a chemical reaction, let's say you have N2O gas, and that becomes N2 plus O, and these are both gases. Your rate law for here, and remember we only care about the reactants, your rate law would be K times the concentration of N2O. However long it takes for N2O to decompose into N2 gas and O2 gas, that's how long it would take for that rate of reaction to occur. So this is directly proportional to your products. The rate of N2O concentration decomposing is directly proportional to the rate of appearance or the formation of product with N2 and O2 gas. In a higher order reaction, we have the amount or the moles of your reactants to consider. So let's do an easy one like water. 2H2 plus O2 gives you 2H2O. In this reaction, we have two reactants, and the rate or concentration of those reactants will affect the rate. So the rate law for this would be the constant times the concentration of H2 times the concentration of O2. However, we're missing something here. This 2 plays into effect. This 2 means it takes double the amount of moles of H2 than O2 to make H2O. So you need twice as many H2 and O2 to make H2O. So we have to include that in our rate law by making that coefficient an exponent. This is a higher order reaction because the rate of H2 is not directly proportional to the rate of H2O formation. It's the rate of H2 with this added exponent in there because of the ratio between H2 and H2O. Okay, so that plays into effect, and this is why this is not a first order reaction, but a higher order reaction. Overall, though, finding the rate law is kind of simple. You have to take into a consideration the coefficient and the number of reactants you have, okay? Next, we're going to talk about a reaction mechanism. This is where things like rate laws get a little bit more complicated because life and chemistry is not as simple as it seems. Reaction mechanisms is a series of elementary reactions. An elementary reaction is a reaction in which the reactants become products in a single step. That's what we're used to. But in real life, like we talked about, reactions don't occur in a single step. They happen through a series of steps, and that is what we touched upon with Hess's law, and that comes back into here, where rates of reaction occur through a series of steps. So this is a 3-step process to make your net or total reaction. And so we use Hess's law to figure this out, and we can use Hess's law to come up with the enthalpy or the energy for this reaction. But for reaction rates, we want to know the whole mechanism, because the whole mechanism tells us sort of a story. And that story here is that this guy is made on one side. Over here in reaction 2, it's a product, and then becomes a reactant for reaction 3. And so they eventually cross off, but what this second step now becomes is an intermediate step. I'm going to trail out there. It's an intermediate step. It's not really shown in this final product or net equation, but it's needed to have the reaction mechanism occur. Graphically, what it looks like is this, where you have your three different reactions occurring in a mechanism, and then you have your intermediates forming here and then being used up. So we have your reactants being formed in the first one, and they're forming into products. Those products are then used as intermediate reactants for the second one, and that becomes a product. And then those products become an intermediate for the third reaction, which is then you have your products here as your end. Okay, so reaction mechanisms are important for reaction rates because, as we talked about, reaction rates can be fast or slow, so the whole mechanism can be fast or slow depending on the individual reactions. We'll talk more about reaction mechanisms tomorrow because they're a little bit more complicated. Other than that, have a great night.